My talk is entitled Floating to New Heights, a Nanoscale Acoustofluidic Technique for Isolating Extracellular Vesicles. This is meant to just be a short talk, but I want to give a brief primer on acoustofluidics in general, and then talk about some of my work on extending acoustofluidics to the nanoscale for isolating EVs. So just a little bit about myself. I'm originally from Philadelphia, Pennsylvania. I'm a huge football fan. Go Eagles. I did my undergrad at Penn State University in central Pennsylvania, and I had to give them a shout out because they're currently playing in the college football semifinals. So I'll be watching that. It's actually going on right now. So very exciting. Where then I moved down to North Carolina and did my PhD at Duke University in Dr. Tony Huang's lab, the Duke Acoustofluidics lab. And after graduating from Duke, I have since moved across the country to Santa Barbara, where, as was mentioned earlier, I'm currently working with the stem cell biologist Max Wilson, using some acoustofluidic techniques to study stem cell biology. But the focus of my talk is going to be about acoustofluidics in general and the work of the Duke Acoustofluidics Lab. So for those of you unfamiliar with acoustofluidics, in its most simple definition, it can just be described as the integration of acoustics and microfluidics, or devices which manipulate fluids at sub-millimeter length scales. One of the most per capillary, and it flows across a lateral flow assay and can detect the presence of certain analytes, whether it be antibodies. Pregnancy tests are also another very commonly used lateral flow assay. But I think a lot of people hear microfluidics might not necessarily know how familiar they actually are with them. But there are two general approaches for generating acoustics waves to integrate acoustic devices with these microfluidic devices. The first being bulk acoustic waves, which if you've ever bought a piezo transducer, these are the acoustic transducers that people are most familiar with, where you can see it vibrating in thickness mode or shear mode, most commonly in thickness mode, but this is where you can actually see the transducer vibrating, and it can be at audible or ultrasonic frequencies. And then on the right, there's another mechanism called surface acoustic waves, where you actually deposit metal electrodes called IDTs, shown here on the right, onto the surface of a piezoelectric substrate. When you apply an alternating current to these electrodes, the surface of the substrate will deform. And if your kind of input alternating frequency is matched to the wavelength of your electrodes, you can generate these surface acoustic waves which propagate along the surface of the piezoelectric substrate. In the Duke Acoustofluidics Lab, we worked a lot with both types of devices, and shown here on the left is a typical bulk acoustic wave device where that bulk transducer is actually bonded to the bottom of a microfluidic chamber. And on the right, you see a because for dealing with nanoscale particles, which I'll get into a little bit later, but you can generate much higher frequency acoustic waves with surface acoustic wave transducers, which are much better for manipulating smaller particles as opposed to bulk acoustic wave transducers. And what is the kind of reason for that? So the general operating mechanism of most acoustofluidic devices is to generate a wave within a microfluidic channel. And when you have a standing acoustic wave, you have pressure nodes and pressure antinodes. And if you look at the kind of force balance on particles within this channel, they will be directed by an acoustic radiation force towards the pressure node. This acoustic radiation force is governed down by this FR equation down here, which is a function of the particle volume and inversely proportional to the wavelength. So as we get to smaller and smaller wavelengths or higher and higher frequencies, we actually increase the acoustic radiation force. It's also a function of this acoustic contrast factor, which is shown here, which is a function of the compressibility and density of the fluid and the medium and the difference between the two. In general, the force opposing the acoustic radiation force is known as a viscous drag force, which is proportional with the radius of the particle. All this is to say is that we have this basic mechanism where larger particles experience a larger acoustic radiation force than smaller particles, so they'll migrate to the pressure node faster than smaller particles, which makes it really easy to perform size-based separation. One of the things that the Duke Acoustofluidics lab has pioneered is also exploiting differences in density and compressibility, and also very small differences in the sizes of the particles. And what do they use that for? One of the first applications that it was used for was for isolating circulating biomarkers. So circulating tumor cells are very rare cell types that are released from the primary tumor into circulation. And the thinking is that for kind of non-invasive diagnosis or early diagnosis, if you can isolate these circulating tumor cells with high purity, you can get a really better insights into early stage cancer progression. The issue with it is they are extremely rare, so there's only 1 to 10 cells per 10 milliliters of blood in most cancer patients. And this compares with the 1 million white blood cells per milliliter of blood and 1 billion red blood cells per milliliter. So you're really trying to find 1 to 10 per billion cells, which makes them really difficult to isolate. In addition to that, they're fairly heterogeneous. There's a lack of highly specific markers for CTCs. They're generally larger in size and have a lower compressibility and lower density. They also are some membrane proteins that you can use for isolating them, but again, they're not highly specific. Well, when initially developed, these acoustofluidic devices were mainly used for manipulating cells, but we wanted to shift to the nanoscale to take advantage of these extracellular vesicles that are being investigated for their use as a circulating biomarker. So small extracellular vesicles, SEVs, sometimes called exosomes, are 30 to 150 nanometers in diameter, and they contain different nucleic acids and proteins and biomolecules from their cell of origin. They participate in cell-to-cell communication, and they're highly abundant. So there are 10 to the 7th to 10 to the 9th EVs per mil of blood in comparison to other circulating biomarkers like circulating tumor cells, which only have about 0.1 to 1 circulating tumor cell per mil of blood. In addition to that, they're found in all biofluids and are being extensively looked at as biomarkers for neurodegenerative, autoimmune, and a variety of different tissue-specific diseases. But in kind of moving this from the microscale to the nanoscale, that was kind of my goal when I first joined the lab. And, I obviously know that they're 50 nanometers in diameter, but I didn't have a good intuition of how much smaller that actually is than a cell. It's 400 times smaller, but I always like to come up with analogies to really help myself visualize this. So if you took a basketball, which is about 24 centimeters in diameter, and made it 400 times smaller, it would be about the size of a grain of brown sugar. So you can imagine the difficulties that would be involved in trying to develop a technology that can manipulate with high precision a basketball and a grain of brown sugar. In kind of coming up with the parameters, under identical conditions by this force balance, a 100 nanometer particle will experience 1 million times less force than a 10 micron particle. So how can we increase the acoustic radiation force? There are two primary approaches that we take to do this. One is increasing the pressure amplitude, which is a function of the input voltage that we apply to the electrodes. But there's actually a maximum kind of value that we can achieve here because our piezoelectric substrate eventually cracks when the amplitude gets too high. The other thing that we can do is through nanofabrication techniques, fabricate very, very thin transducers to decrease the wavelength of the acoustic waves. And right around the time I was joining the Duke Acoustofluidics lab, they had published this very interesting paper about isolating exosomes directly from whole blood using a two-unit kind of sequential filtration strategy, where the first unit, which operates at 20 megahertz, removes all particles larger than 1 micron, so all red blood cells, white blood cells, and platelets. And then the second unit separates out these larger apoptotic bodies and microvesicles from the smaller exosomes. And this technology was very powerful, very impressive. We can do it, compared with like the traditional techniques like ultracentrifugation. It's much more automated. It's much faster. But one of the primary limitations is that when we isolate these exosomes or EVs, there are still smaller proteins mixed in with that sample, which, depending on the application, may or may not be okay. So what I wanted to do was come up with a way to separate the EVs from those smaller contaminating proteins. What I came up with is this technique called flocculation via orbital acoustic trapping, or float, which uses a thermoresponsive polymer combined with these high frequency surface acoustic wave transducers. And our device is shown here. We actually create a mini droplet centrifuge. So the focal region of each of these transducers are slightly offset so that when we apply a voltage and turn these transducers on, this droplet in the center will start rotating very fast. The specific application that we were looking at is to isolate EVs from urine samples. And the reason for that is because of the presence of this THP or TAM horsefall protein in urine. It's the most abundant urinary protein. And under standard centrifugation protocols, what this protein does is actually forms like a mesh-like network that actually precipitates out of solution and traps a lot of the EVs with it that end up getting discarded as waste in the intermediate centrifugation steps. But you ultimately want to recover as many of these EVs as possible. So I mentioned that we use a thermoresponsive polymer. We tried to use NiPAM, which is a temperature responsive polymer that's highly biocompatible and used as a flocculant for other applications like mineral recovery. And its basic mechanism is that under this lower critical solution temperature, or LCST, of 37 degrees Celsius, it is very hydrophilic. And as you raise the temperature above that point, it becomes hydrophobic and will start to aggregate together. So you can see just NiPAM and water, images of it here below and above the LCST. When it's above and very hydrophobic, it's very opaque. And below, you can't even tell that it's dissolved in solution. So what we did was we take a urine droplet, we mix it with this NiPAM, which has a cationic functional group on it to allow it to absorb to the surface of the EVs. When we place the droplet with this NiPAM solution on our droplet centrifuge and turn it on, the droplet begins to rotate and controllably heat. And what happens is once we get above 37C, all of the polymer on the surface of these EVs want to grab onto each other. And it starts to form these flocks that ultimately aggregate into a single pellet that we can remove from the droplet and analyze downstream for different applications. So in characterizing the droplet centrifuge, we can see here that the kind of ultimate temperature that it reaches is a function of the input voltage. And we wanted to choose an operating temperature that got us over that temperature of 37C without going too high. So we chose 10 VPP. Here is kind of the real-time temperature measurements in addition to corresponding videos where we mixed 50 nanometer fluorescent polystyrene beads with a NiPAM and turned the acoustic waves on. So at the early stages, points 1 and 2, you can see that you can barely see the fluorescent particles because they're so small. But as they start to aggregate and come into contact with one another, the fluorescence intensity is enhanced. And we ultimately are able to get the majority of these 50 nanometer particles to aggregate all into one central flock. We kind of conducted these across polystyrene particles across the size range of EVs and show that it's capable regardless of the size of the particles. And importantly, we wanted to incorporate this into a real world application aimed at isolating urinary EVs and comparing it with the ultracentrifugation technique. So in part F here, I have, this is nanoparticle tracking analysis of fluorescently labeled urinary EVs that we have. You can see the size distribution And then we actually aggregate them together and they form this pellet. We can resuspend this pellet in another solution and measure the size distribution. And that also gives us an idea of the yield of the number of particles that we recover from the initial sample. Our yield is around 91% of the recovered particles. We do see that there's a slight increase in size attributed to, in this case, the polymer is still absorbed onto the surface. But most importantly, in I here, what we see is this ability to selectively isolate. Here is Western blot analysis results for THP and two EV markers, CD63 and TSG101. The initial urine sample contains all three. In our isolated sample, we do get some THP, but we get a high yield recovery of the CD63 and TSG101. And most importantly, in our kind of waste sample, so after we remove that pellet and run the Western on the remaining fluid, there's nearly no markers for the EVs left behind. And then we wanted to show that it was compatible with some downstream functional readout. So we conducted RT-qPCR on two different microRNAs, MIR21 and MIR204, and showed that our yield is much higher than that achieved when just using the standard ultracentrifugation protocol. Because as I mentioned earlier, that THP network actually traps and a lot of the EVs end up getting tossed out in the waste in the intermediate centrifugation step. Um, so overall, float is a rapid technique for the enrichment of EVs or other nanoparticles. It enables very high yield recovery and selective recovery of EVs from contaminating proteins. And it's also compatible with low volume samples, making it a promising approach for point of care applications. Going forward, some of the ideas that we had are to incorporate this thermoresponsive polymer, NIPAM, into our continuous flow device to enable a kind of all-in-one solution for EV isolation from unprocessed biofluid samples. So you can imagine kind of a third module that would then separate the EVs from soluble proteins based on kind of that controlled heating aspect of the acoustic waves. In addition to that, we used a very basic version of NIPAM for this that just had a cationic group added to it to allow the molecule to absorb to the surface of the EVs. But you can actually do some polymer engineering and have functionalized thermopolymers to only allow the polymer to bind to maybe specific surface markers to enable enrichment of specific subpopulations of EVs or any kind of bio-nanoparticle of interest. Quickly, I'd like to acknowledge the Duke Acoustofluidics Lab and my advisor, Dr. Tony Huang, and then I'll open up to questions and just play really quickly the video in real time. Let's see if this will play. Ooh. Here we go. This is actually the fluorescently labeled EVs being concentrated in real time. And you can see the droplet is rotating at extremely high speeds. We surpass that kind of LCST, and then the particles start colliding in, these urinary EVs start colliding into one another. And then we can come in with a glass capillary and actually remove these EVs and transfer them for downstream analysis. So there it is. There's the glass capillary. We can remove it. And
my talk may be a little bit out of the microfluidic areas. So I will talk about from Alice to Alita, the adventure of a self-powered smart system. I'm from Peking University, located in Beijing. And let's see. So I was joined Peking University 25 years ago. So it's a pretty long time. So that time everyone was working on MEMS. So MEMS, everyone knows these pictures is sensors and actuators in the, micro nano scales. So that time we named this as micro electromechanical system. But from my side, I make another kind of type of this maps is miniature everything and make it smart. Because not only, try to make something really smaller, but also, want to make something very smart. So yeah, since 25 years ago, I was working in this field and try to make some fun. You can see this is my group. So it's Alice Wonder Lab. So because my English name is Alice, so I want to make something really with joy, in fun and interesting. So my lab was Alice Wonder Lab. one lab. So with all these young, students and really, really great collaboration with many of my colleagues and friends. So we make something interesting. So today I'm going to, give you some examples as, from Alice to Alita for this topic is right because name link and also in last, 3 years. So everyone was talk about AI, AI, AI. You couldn't amazing these words. So from my side, I'm thinking, what AI meanings really in my research and what we can do for this AI. Let's look at these two figures. It's myself was a carbon-based life, right? Yeah. So later in the future, the artificial intelligence will be a silicon-based life. So from this carbon-based intelligence life and to a carbon-based to a silicon-based, intelligent life. So what we can do and what we can contribute from our own research. So I think in my research, our three kind of keywords were related, with this future artificial intelligence. First is self-powering. Another word is active sensing, and the third is about smart system. uh, why I choose these three keywords? Let me explain this first. So let's see that Alita. So this is super artificial intelligence. So if it's not in real, but will become in reality in the future. But think about this girl, why it's super powered because it can generate the power by herself. So that I'm thinking we need to power the future, artificial intelligence system. So what's the best way, to use battery or use the long wire with a long tail? That's not the final solution. So if we can, contribute some technology from power by themselves, that would be make more sense. So 12 years ago, so we started this cable generators. So this was quite interesting story. So because Professor Zhonglin Wang from Georgia Tech that time, he was invented the triboelectrical nano generators and published the first paper on his own journal, Nanoenergy. So I met him in Italian on conference. So he told me this, but in the very beginning, I really couldn't believe it because, triple generators, like, you use the friction of this kind of very normal very normal motions, all these things, it can generate a high power. So that time at the very beginning, I couldn't believe this. So, but as a scientist, I think, if you don't believe it, you need to try by yourself, see if this was a truth. So after the meeting, and the Italian in the June, 2012. So I back to PKU and I start to try, see if this can work. This was the first the examples we did these triple generators in my or Alice Wonderlab because that time I have a lot of samples on my hands as for this kind of micro nano durable structures, a texting surface. So I made a lot of these samples. So that time I want to use it, for other applications. But with this, I think okay, let's try with this micro nano durable structures and make a simple, sandwich triple generator, see if it can work. So we make this very simple structures. You see the double layers with micro nano durable structure there in between. It's a couple layer used as the electrodes, also as a function for this, movement, the frictions. So this triple generators, the first generation was work. See the output of this, you can see the current, the not only the voltage can be go up to 400 volts, also the current can be go to 100 microampere. So this is a big step. This can generate real powers, and this can be used as continuous output. can be converted to more than 10 volts. So that makes a lot of sense because many of these micro nano chips or devices or sensor activators can be turned on by this, output by this simple, triple generators. So since that time, we start, to focus on this topic to make the nano generators, to see if we can make, many kind of helpful or usable generators. So this was the simple fraction surface, triple generators. Why we make this? Because one of my students was talking with me. He said that Alice, all these complicated structures with double or triple or even multi-layer surface is, a big volume also. Not only the volume, it's also need more space. But most of the applications will be focused on all these, micro or nano devices was based on touch screen, kind of the ends. So if that possible, we can develop something, by this touch screen in the devices. So that time we make these micro nano durable structures with transparent, materials and put on the surface of this screen and then can be generated powers. So this was the first, single friction surface triple generators. This really, really exciting and, push our research moving forward to generate the power in a simple way and also with a high output. So this was for the generators with a triple generator and piezo generator hybrid together and to make a much larger output. So you can see these simple structures with micro nano durable structure to make R-shape generator. So this can harvest the power, the movement, not only from the friction, the touch and the screen, the touch and the departure, also can generate the power by this movement, by the piezo. So this can enhance the output. This wave shape, the structure with multi-layers also can generate the power from triple and piezo. So this makes the output more reasonable and for applications. And this was the hybrid structure with triple generator with a magnetic, magnetic electrical generators. So everyone knows a magnetic electric generator can have a larger, current, and the triple one can have, larger and higher voltage. So this can be, combined together and to applied in many, applications for this. So like, the wearable and the wearable devices. So all these kind of applications also can be, move forward into this this very nice structures with a three-dimension you can movement. So this was example for the solar cell. So we make these mirrors on the surface and this tunable, tunable structures can be, follow the light in the whole angles. So this can be covers the energy from the solar, and also this can be harvest the energy from the triple. So this could also can be enhanced application in this outdoor devices. So my group has many of these hybrid energy harvesters and for different applications, and all this surface and looks very interesting because all covered by our MEMS fabrications. So it can be mass production and also can be very cheap and very convenience for everyone to follow this structure. And another kind of step forward is for how to use, these structures can be as sensors. Like we see from Alita, you can see that Alita was super because not only Alita can, can uh, be functioned, but also can be super sensitively, response to the outside and they make decisions. So by his custom this clothes, you can see that this was a super sensor network. So with many super sensitive sensors nodes on it. So that time we think is that possible use micro maps for sure as for the sensors, but another thing is that possible can we combine this, micro generators with these sensors, because this has a good kind of principle. You see that by these, triple generators also can be think about like electrifications. When you touch on the surface, get on the clothes, you can generate the electrons on the surface, and also, these electrons was rich information of the output. So this can be used as a sensor, active sensors, because it's, signals was based on your own, movement and all these, reactions. So this was the first example we use this principle to make analog smart skin. Why a name analog? Because you see the structures is on this. This was original structures. You can see that it's four electrodes, and on the flower, this was the demo. You can see that it's totally transparent, and the electrodes was on the edge of these devices. So on these large areas, just need four electrodes. Then you can get, the precision, a very precision location of the output, the force and the locations. So this meanings, really helpful to use as all these smart skins, like on Alita, if you can put this transparent, the smart skins, on the surface, you can easily to get many informations by this, and just don't need many electrodes, just need four electrodes. In by the calculation, you can easily, to get many informations from this. So this was really good. So I remember on one of the news for this publication that now the robots can feel the outside. So that's exactly what we want to do. Make all these, robots or, the artificial intelligence later, it can really feel the outside, feel the environment. So this was the first sensor we made. Then based on this, we're moving forward to, get some more exciting devices or sensors. This was non-contacted electro skins. So because just now that one you need to contact the surface. So many things you don't want to contact, maybe remote control, remote feelings. So is that possible to make it as a remote feelings? Then this was a special design with surface, patterns, different treatment. So we make this, this non-contact electro skins. So this non-contact electro skins give us more space, can potentials for application of this, kind of sensors. And this was a game designed by the students, can be, remote play these kind of games by themselves. And this was a 3D multifunction electro skins. The principle is all the same, but the difference is this was a multi-layers in the 3D dimension. So this 3D dimension can get you more information about like signatures. This use this as an example, so will be easily to understand. When you use the signatures, this was not only by the patterns, also have information, by the force. So if you can detect the force in the 3 dimension, this will give you more kind of precision or accuracy, for this detection. So this 3D, multifunction sensors was really useful for this kind of applications. And this was another kind of smart, very smart design. I like this very much because this was use the patterns. Now, many times you can see that, you want to get more kind of precision information, you need more electrodes. So like in our lab, we not want to, just increasing, the electro, kind of numbers. So this will be kind of very complicated. So is that possible to design something, with limited electrodes and you can get more information. So this was by the Archimede, design. So just use 5 or 6, electrodes. We can cover more than, 200 angles, and this can be get output information is more kind of rich and how to say multiple informations on this. So this is really great can design, but this also can related to these pictures because there comes multi kind of data, yeah, really big data. So you need the algorithm to enhance your output and to calculate all these informations. So that time I use machine learning, the machine learning technology to enhance our hardware. So use software and the hardware together, to make get more information. So the last year you will remember that the Nobel Prize go to machine learning, which exciting events also can use machine learning to enhance your research. So it's really kind of exciting and great, integrated of this kind of new tech, not the new technology, but this, topics into your own research. So this also help us a lot, for this, systems. So this will come to the last part for the smart systems. Actually, we see that you have the, you can power yourself, and you also can, have a multi-function, the sensors on, by this simple principle and use the soft or flexible materials. And the last part will be, if you really want to make it function, you need to make like smart system. It's not just the sensors or just the, actuator or something. It must be a sensor, a smart system can be working together. Let's see, we want to make this system, we need some kind of more exciting technologies because not only one sensors, not only one actuators, not only one generators can be a system. You should to integrate them together. If you want to integrate it together, you need a complex system. But the thing is that possible to make the system not that complicated and also can be reversible and reconfigured by this. So that time we think about we need to use one very powerful materials, magnetic materials. So we synthesize this hard magnetic graphene, nanocomposite in our lab. And this, we shot as HMGN. This was, composite has very special kind of functions. It can first it can be enhance the electric connections. So you need multi layers. You need multi sensors or devices on the surface. So if you can use this magnetic aided electrical, electric connectings, it can easily to, save a lot of space and also can be solve the complex in line and all this works. So this was the first part we use is magnetic aided, materials. The second is we found that surprisingly, this magnetic, materials also can enhance the sensing, performance, the sensors performance. So I will give you some examples here. First is this was can be really enhance, this self alignment and this very high reliable connections by this, magnetic materials. You can see that this was a different electrodes and with magnetic materials, it can automatically, mounted on the right space and the right location. Also, the electron connections was very stable and very good, resolutions for this wire connections. So this was the first part of this. The second part is you can see these reconfigurations by these materials. It's really flexible and also stretchable. We make it stretchable too. And with these, materials or this substrate, easily you can make different sensors and actuator to mount it on this, substrate. And also you can easily to change, the functions with different the sensors like this, all this, standard design with connections of electrodes, and you can reconfigure reconfigurable the sensor and actuators on this simple structure and on this, substrate. So we tried many different, sensors, more than 5 or 6, kind of sensors on this. And this was the schematic design. You can see that 2 electrodes device and 3 electrodes devices on the simple design on this, and you can easily to mount it on this. And this was a different sensors, and this was a real product, and we fabricated this, on the polymer or polyamide, and this can be transparent and flexible and stretchable, the devices. So this was with 2 electrodes, 3 electrodes, and this was sweat sensors. You can say with 7, electrodes. All this can be the very standable, models. Then use this, you can easily to change it to others. Let me give you examples, for this application. You see that just now that was examples, and this was a real, applications used on the artificial intelligent robots' hands. And on these robots' hands, they have many different. We have about 1, 2, 3, 5, 6, 7 sensors, and all these sensors was mounted on different, place, because it's different place, like, in the center of this, easily to harvest the sweat. On other place, you need the force sensor or temperature sensor or gas sensors on different other parts of that. The connections of these wires and all on the different space. Then you can see this was the details of different, sensors. This was this was the structure of the whole system. With this whole system, easily you can get, different sensors, and also with the harvest, the energy harvest inside. So this was really can help you to, support the self-powering, and also get different, parameters about outside, and also can get more information on this. And this this was a real kind of data or examples how to make the detections. Here you may ask the questions is that you have so many sensors on the on this single substrate. So maybe the sensors and they cross talk a lot, not that super accuracy will be a question of precision, will be some questions. So here we have some strategy to solve this coupling issues. So we design the system with some thinkings about to decoupling of these multiple sensors. So we also use algorithm, to solve these problems too. So on this structure, on this robot hands, we have seven sensors and generators on that. So it covers physical sensors, chemical sensors, the biomarkers, and so we're different. So it's decoupling by the system design, also by the algorithm, afterwards the data processings, to solve this problem, then can get all these different parameters on the same structures. This was another example. So we try to move on mass production. So this mass production, the sensors is by this method fabrication too. You can see this, this tactile sensors was last year we make this collaborate with another professor is also my PhD student Meng Di Han. As design based on this MEMS sensor and also by this simple structure and simple principle, and also for the you use different materials to make these tactile sensors in the mass production. Super smart sensors in this structure is a 3-dimension. Just now, all the sensors on the surface on the on the robot hands is 2D dimension, and this was a 3D dimension. This can be harvest the information from the 3D for this tactiles, and you can see this was different the design of this, but by the simple fabrication too, it can be the whole wafer level fabrication of this really mass production and big array, the large array about these sensors. And this 3D tactile sensors is very easily to applied in many in different kind of application, also put in different location of the robots. And this was another high density design for this sensors, this tactile sensors array. You can see that is millions, on a very small kind of surface, on a very small on a very small space. So, but this can be enhanced robot hands, for the tactile sensor arrays. So very much, so they can get very sensitive informations, and especially it's 3D, informations on this. So this was a large area application. You can see that this design was also follow, the previous one, also uses, multifunction and reconfigure structures, to found all these, sensors to put all these sensors on the substrate and to easily, to get more high resolution and high performance of the sensors. So this was the application of that. You want to put it, on different kind of coverage service. So this service, they need more kind of flexibility. So you can use this 17 design to make it flexible and to make a more kind of precision on different locations. So another as in the future, we want to enhance all these sensors and this kind of substrate and with generators and also actuators on the same system. This will be a all-in-one smart system. This was a long-term, kind of work in our group, and also I think this will be a long-term, achievement to be a real artificial intelligence, by the small sensors and actuators in the system. So this was in my group, we really can focus on these topics. So in last, a few years, we really published several, not only the papers, we also published several books on this for the smart system and also for this nano generators. One was in Chinese, another two was in English. So if you are interested, you can easily find it online. All these works was already in these books was well explained and concluded.